next speaker is Dr. Giovanni Grasselli from the University of Toronto. He's going to tell us his lab testing program and how it's going to change your thinking about how to run an energy resource business. So please welcome Dr. Grasselli.
So thanks a lot. And it's been always a pleasure to be here. And finally, after too long, we're in person, and I think everyone is acknowledging this fact, and this is good. So today, what I really would like to talk about is how we can try to add value to the energy industry through laboratory testing. And it's my pleasure to present the work that we've been doing for the past 2.5 years, probably at the University of Toronto. So one thing that has been mentioned today quite extensively is that, well, the subsurface is fractured, and knowing the fracture geometry is important for really a lot of different application within the energy world. So fracture are really crucial for a flow in a low permeability matrix, like shale, like actually granite, if you're looking at harvesting heat from underground. And also important when you want to inject a fluid or a gas like a CO2 underground, you need to understand where this gas can move, and not just in the permeable media, but also in the fracture. And one thing I want to remember, to remind everyone, is that fracture for fluid are extremely important, are basically highways to the fluid. So, and there's a so-called the cubic law that tells you that the transmissivity of a fracture is actually function of the cube of the aperture. So that means that even a small increase in aperture means that the permeability, the transmissivity of that fracture is going to increase by a cube factor. So it's really, really, really important. So these pictures, I took those pictures on the outcrop not far from here on the Kananaskis, and these are picturing the outcrop of the Montany shale. That is one of the most rich place in Canada. And when you look at the outcrop, you see that you can identify a lot of fractures, incipient fractures and bedding planes. So the fractures are everywhere within this formation, for example. And when you try to look at modeling and you try to see how the fracture is propagating in such a medium, really what you see is that the fracture direction and trajectory will change as function of the normal stress, the in situ stress that is applied. And you can go from pseudo-horizontal to vertical. But what you notice is that no matter what you are doing, the fracture play a key role in the geometry that you are obtaining during the fracturing process. So, oops, go back one. Let's get Superman away. So one thing that has been proposed, for example, by Professor Dussault, is that well, when you inject, we need to take to really take advantage of the fact that those are fractured. And when you inject the fluid, you create an opening, you create some slip, you can create some rotations. So in the picture on the top, you see really what again the Montany shale outcrop looks like. So not many in May actually we went on this outcrop with a drill, and we want to core a sample out of a particular horizon on this outcrop. We start coring, and what happened was that look at the last picture on to your right. Well, we're coring vertical, and the fluid we're using was actually coming out from the side outcrop. So why? What was happening? And that is where I really would have loved to be Superman, with X-ray vision, being able to see what was happening there and why the water was coming out from there. So now, well, I'm not Superman. None of my students is Superman. So what we did, we went to the lab and we actually took advantage of a facility that is available at the university. And in particular, we have a unique system, a loading system, is a true triaxial system, was actually developed by Professor Young about 20 years ago almost, was design. And that allows us to get a cube of rock of 8 centimeters, so basically this size, and to bring that cube of rock to the stress condition that has experiences in the field. Then what we did, we modified this system and we added the capability of using a mini packer to reproduce what would be the completion, what would the rock would see during the completion on one single stage open hole. And by doing that, we think we can reproduce the process that the rock locally would experience during the hydraulic fracturing process. So, but the unique capability of this loading system is that actually the vessel is able to monitor the acoustic emission that are a proxy for microseismicity on that block. And we have basically 18 sensors that will cover the entire volume. And in addition to that, we can monitor what is the seismic velocity P and S waves along the 3 axes of the cube. So basically that should give us the equivalent of an X-ray vision of what is happening during the injection and the fracturing process. That was the thinking. So now we got our cube, we placed the cube with at the stress that were indicated by our industry partner at the reservoir level. We drill our mini well horizontally, so parallel to the bedding plane as it is done normally in the field. And then we start pumping. And at that point, you can see that you have your cavity filling, your pressure rise, your breakdown pressure, you regain pressure, and then you have all that zigzag fracture propagation. And each drop in pressure is normally a proxy for the crack that is basically keep on propagating. That's quite amazing. The one we are doing that, we were thinking that, well, this looks really like what we've been witnessing in a fracking room. That's great. So now let's go back. So theory is telling us, when you study, that when you have when you inject fluid in a medium under polyaxial, so sigma 1, sigma 2, sigma 3 stress conditions, you basically create a fracture that opens against sigma 3. So the minimum principal stress opens. In this case, what we expect is a vertical fracture that open against sigma 3. However, what we start noticing was that the water was not coming out of the planes at all. It was actually coming out from a plane that was parallel to the bedding. So the induced fracture was actually not following what the textbook is telling us. So that was a little bit puzzling. Was a mistake, was not. Let's try to do differently. And we did actually 10 tests, not one. And I'm presenting only one. Results are always the same. So, well, what can you do? Let's look at the cube, because the rock is there. Let's see what is happening. So, and what we notice is that looking at our data, one side is opening, one side is closing, and those extensional measurement, displacement measurement, is a little bit puzzling. So I'm moving the wrong side. So now let's look at really the rock. What we start noticing is actually from the injection well, we have fractures that are developing are parallel to the orientation of the bedding planes. But more interesting, we found on the surface some echelon fractures that are a clear suggestion that the process was not as simple as we thought, because it means that an echelon fracture is a proxy for shearing taking place. That is even more puzzling. So let's get back and let's look at the data. And the data as telling us, you can see opening if the graph moves down and closing if it goes up. So we can see that when we are looking at the plane sigma 1, sigma 3. So basically, let's see if really it was opening along against sigma 2. And yes, our measurements, the displacement measurements, LVDTs are telling us that is opening against that direction. Again, puzzling, we shouldn't do, which is probably this cube, it's not read the textbook, or maybe the textbook is wrong. So what is interesting also is that at the end of the test, there was clearly a residual opening that was left. And generally, residual opening means also that some shear took place, and that residual opening is a sort of an indication that some shear displacement took place, despite no shear stress was applied. And as I said, we thought we had our X-ray visions. We thought that our acoustic emission sensor would have allowed us to really see the process, but we could find only one A event. That means that all this cracking, all that process was super silent, only one crack. And industry is relying on microseismic survey to really understand where the fracturing is going. And we had all the sensors, much better coverage than the field. We couldn't see anything. So even more puzzling. So now I really would have loved to have the X-ray vision of Superman. So what we did, we decided to actually image the cube. Let's look how the cube can look like. And what we did, we used a combination of X-ray micro-CT and a serial section reconstruction. That is a destructive method that allows us to measure and to map all the fractures that have been that are present in the cube. And the serial section happens after impregnating the cube with a fluorescent dye dissolved in epoxy. So by doing that, we could reconstruct what was the fracture network that we created. So now, if we look and you are modeling, generally you get only in the model, the hydraulic fracture is a penny shape fracture that develops open to sigma against sigma 3. What we found was a very complex fracture system with open bedding planes, presence of a natural fracture, and some fracture that were definitely hydraulically driven, more or less open against sigma 3, but not really. So the advantage of having digitized this data is that we can not just observe, but we can start getting really quantitative analysis out of these points, of these planes. And what we could look at, divide them in classes. So we can assign them in bedding planes, opening, parting, natural fractures, and hydraulically driven fractures. So what we notice is that we could really look at what is the percentage of this stimulated rock volume and assign those percentage to these three classes. What we notice is actually basically 90% of our stimulated rock volume is not really hydraulic fracture, but are bedding planes and natural fractures, where bedding planes take about 60% of the total volume. That that is something that is interesting, I think. So by having access to this information, what you can is looking at the fracture domain. We can look at how the fractures are connected. So the connectivity, and we can also measure what is the aperture, and with the connectivity and the aperture field, what we can is start using this as an input for a numerical model that you can use, for example, to look at the production and try to understand what area of your stimulated rock volume is producing, and potentially we think we can use this type of information to upscale our learning to be used in classic reservoir simulators. Now, and we can do much more. We can look at, for example, the aperture distribution. And again, what we see is the aperture of the bedding planes results to be higher in average with respect to all the other families. That means that the bedding planes, they seem to conduct much more fluids than the other families of set of fractures. And again, I remind you, the cube of the aperture is directly a function of your transmissivity. And well, what we are working also is looking at the influence of roughness and all these other parameters that might help in actually increasing and having more information. So at the end, what it seems out of all these tests is that the parting of bedding planes really dominate the fracture network, and is something that, to my knowledge, is fully disregarded by industry so far. So the other thing we know is that these fractures are growing, but we couldn't really hear them. So microseismic are really missing. So the point, it looks like that the key aspect of your hydraulic fracture is a propagation that is aseismic. So and the bedding plane actually have a very low activation that could also explain what are the strange, I would say, results that you obtain from the field. So shall we go bedding planes, or we should keep parting of bedding planes, or we should continue thinking about our penny shape fractures? That's a question. So now, one of the big problems we have with our test is that, and everyone will ask, is the cube is small. So how you can upscale this volume to a larger scale? So that is what we're heading now. We're looking at a much larger scale within the size of the laboratory. So it's the mega block experiments that we are starting. So we obtain and we quarry 2 blocks are 70 centimeters. So basically this high cube. And they are now sitting in the lab, and we're going to reproduce a similar experiment in the lab with the same rock we tested inside our polyaxial. And the idea is to try to see if what we observe at the polyaxial in the 8 centimeter cube is reproducible at larger volume. If that is the case, we don't see why that process could be further upscale to the reservoir, and we're quite convinced that that will be the case. So the quarry is coming off for here from Canmore, and from the Sulphur Mountain Formation, that is an analog for the mountain shale. What is unique of the mega block is that, given the volume of rock, we are going to be able to equip it with as many as remote sensing tools as we can. And the idea is to acquire as many data as possible to really try to understand even more what is happening during hydraulic fracturing process in layer anisotropic rock. That's actually led me to basically the last. From all this work that has been done by an amazing team at the University of Toronto, What we noticed is that the rock strength, the fraction network, and the fabric anisotropy, and in particular the presence of bedding planes, are critical, but however, are often overlooked by industry, and these are fundamental in understanding how the rock fails during injection. So the key is that the bedding planes are everywhere in any shale formation. It's part of the sedimentation process that those rocks have been created from. So what we think is that, and the direction we are interested in, is really trying to look on how we can take advantage of our understanding of the mechanism and try to better engineer our reservoir. That means that we could also mitigate risk, because one of the big risks that right now industry is facing is, for example, the so-called frac hit type. So what is a frac hit? Maybe it's just a parting of bedding planes or on horizontal features, and by understanding this process might be improve our understanding and also better engineer and reduce the risk during completion. So can we come up with a sort of a frac hit, a traffic light approach that will allow us to be really to improve our completion strategy and reduce the risk? So that is basically what we have been doing and where we are heading to. And in doing that, before closing, I really want to acknowledge our sponsors, NSERC, Energy Simulation, CMG, Geomechanic, and Petronas, and all the students and postdoc research associate that actually did all this work. And that said, I open the floor to questions.
Thank you, Dr. Grasselli. Any questions from the floor here? Hardy, you're ready. No? Yeah.
Thank you very much. Very interesting topic. Actually, I'm very interested in this topic because I'm studying the casing deformation problem. And I also, as Professor Grasselli said, I'm agreed that many people in the industry is disregarding not only bedding plane, but subhorizontal planes. The common assumption is that natural fractures and faults are the responsible for casing deformation. What I see here is you are confirming that hypothesis. I'm trying to state that bedding planes, horizontal, subhorizontal planes have a very significant role. And if you take into consideration the stress states in highly tectonic areas where the horizontal stresses are very high, the hydraulic fracture has the tendency to be horizontal. So it will go through those planes. So do you think that maybe taking into consideration the mechanical properties transition, mechanical property contrast has a very significant effect in this phenomena? Because sometimes I feel that the term bedding plane and histology interface is interchanged in the literature. So how what is your idea about the mechanical property contrast in this phenomenon?
Well, the answer is yes, I totally agree. The mechanical properties, so the strength of the rock is a transversally isotropic type of material. That means that the strength in one direction is different than on a perpendicular direction. And that should be accounted for in any modeling and in any approach. And my knowledge is not many software account for that in their solutions, and that is I think one of the biggest limitations that I would see right now that could be addressed. And so yes, that will lead also to an additional challenge that has been touched during when we're talking about this morning about reservoir simulation and fluid flow, for example, in porous media. You do have not an homogeneous, it's definitely a heterogeneous medium, and is transversal isotropic. And you should use both, because that heterogeneity will sort of make maybe one layer less resistant to opening than another one. And I will also explain why maybe the propagation is not symmetrical with respect to the injection, but is more parting on one side of the well than on the other one, for example.
Good. Radu?
Thanks, Giovanni. Excellent work,
Thank you.
as usual. I have a question about the stress regime. Do you have any other evidence to prove that you are in reverse faulting?
No. No.
So these numbers are just calculated, basically.
These were given at the time by our industry partner. What I can tell you is that because the block was not, so these were what we were given and we used that. So, however, because as I said, the blocks were not obeying to the textbook, what it was written on the textbook, we tried actually to change the stress condition in the lab to see if we would have been able to force the fracture to propagate, basically to open our sigma 3 plane. And the results were...
So basically you put the normal faulting and it didn't actually propagate a vertical fracture?
No, we couldn't. Within the range. I think that changing the range we might be able, but so far the tests we have run, even changing the stress condition, the parting of bedding plane were always the key aspect or results of all these tests.
What I would do if I would be you, if they do any field experiments, like getting a tiltmeter array and the vertical tiltmeter, I mean a bunch of vertical tiltmeters in microseismic, you may be able to identify if you're propagating these T-shaped fractures. They probably are there. I think it's fairly realistic. I just don't trust the reverse faulting myself. But other than that, really great work. Have you planned any like viscous fluids with propants in the experiments? Or you cannot do?
Any what?
Viscous fluids with propants.
Yes, we did propant, no. We tried with the propant, but because of the scale, we need to scale everything, and we couldn't find a fine enough propant during the test. But yes, we use, well, Matt is calling the tide pod experiment. And yeah, we use a tide pod, but the only one.
You didn't see any change in the geometry with viscous fluids?
Not really, but we didn't know. Well, we play only one. We didn't really went for high viscous fluids. No, so there is so in a short answer, we didn't really study what you're asking for so far.
Okay, Professor Grasselli, from your sponsor from Petronas Canada, Shoji said to thank you for the presentation.
Oh,
I do have a comment though. Really happy, glad to see that you're talking the application of your lab work results to energy industry. It's not just oil and gas. Because for example, I believe there's a company in Saskatchewan called Deep Earth Energy Production. They're doing sedimentary basin type of enhanced geothermal systems requiring some fracturing of the formation. But if indeed the fracture will grow to the bedding plane and you get a short circuit through the bedding plane, that's something to watch out for. So really interesting piece of work, and thank you so much.
Thank you.
Oh, sorry, one more question before we close then. Okay.
Doug Beringer again. This is wonderful work, but I wonder if 8-centimeter cube, you're just seeing the initiation part of the hydraulic fracture. So it'll be interesting when you jump almost an order of magnitude to 70 centimeters, if you're going to see some additional things happen.
Well, I cannot answer yet. We hope so, in a way.
And are you going to keep the same size of borehole, so your multiple borehole diameters further out into the rock?
We are still designing exactly how the test will be done. The size of the borehole will be the same. The injection strategy will be the same, just to try to see if the volume of rock around will change the results. Will not be able to use the same stress data we used on the 8-centimeter cube, for a simple reason that the force that will be necessary to load a 70-centimeter cube rock the same stress level, it's not feasible, full stop. So it will be a very, very low stress state.
So the lack of acoustic emissions is maybe not surprising, because in the field, we don't hear most of what's going on with microseismic. There's some lower limit of detection, but also, there's a size distribution of events as well, right?
I know, but I think we are coming up with a sort of an explanation why, and I feel very proud of the results we have been presenting, is that it seems that now it makes sense. Everything comes to all the pieces that are there, have been published and widely discussed and available to everyone. They come into a picture. It's like a puzzle. Now you can start seeing the picture, and by seeing the picture, I think we can start using that picture to better engineer the reservoir. No matter what is right now we're looking shale, but it could be application to geothermal. To tell you the truth, it can be application to nuclear waste industry. Is just the energy and how the fracture propagates.
So I think you're providing a valuable link between remote sensing type things we do in the field and directly seeing what happens in the rock. So that's a very valuable contribution.
Thank you.
Yes, indeed. So thank you, Dr. Grasselli, for an interesting, informative talk. So following this, we've finished all the technical sessions, and there will be 1 hour of poster session.